Hi, and welcome to Amplifier Phase Noise Testing at Mini Circuits Part 2. If you recall, during Part 1, we talked about what is additive phase noise, how we measure it, specifically how we measure it here at Mini Circuits, how to specify it, because we get a lot of inquiries and oftentimes the inquiries are not clear. One of the things we did in Part 1 is we looked at a single amplifier, and we looked at that amplifier in both small signal and large signal regions. What we discovered was that there are certain regions of AM to PM distortion, which when you characterize in terms of degrees per dB, you get a very characteristic shape. And if you happen to be operating your amplifier in that region of AM to PM distortion peaking, you could significantly degrade your additive phase noise. So we stress that what's important is to kind of avoid those regions. So what we're doing in Part 2 is we're going to look at cascaded amplifiers, and we're going to kind of focus on saturated amplifiers or amplifiers or amplifier chains that one may use to drive, for example, the LO port of a mixer, because that's where you want to get the best additive phase noise so you don't degrade your signal coming in. So we're going to look right now in Part 2, we're only going to look at 2 amplifiers in series, and we're going to look at, in this case, 4 amplifiers in parallel. And we're going to look at different configurations, and we're going to see that there are ways to configure those lineups to achieve optimum additive phase noise performance. So before we do that, we'll just go back into a brief test set review. We've all seen this before in Part 1. There it is. It's in our temperature and humidity controlled room. It's on a vibration isolated table. Everything is kind of placed on vibration isolating material. We run our DC voltages into the device under test, or DUT, which is in this EMI, electromagnetic interference chamber. So we shield the DUT from any external EMI influences. We have RF coming out of the instrument into the box through a variable step attenuator and a fixed pad. And similarly, back in, we have a fixed pad and a variable step attenuator. This allows us to control, one, the power level that we set the instrument to. It's very important that we find the correct output power for a specific carrier frequency, because the additive phase noise performance is not the same for all power levels. At least that's what we found. And similarly, when we control the output of the DUT, we're able to keep the input power back into the instrument within a narrow range, which makes the measurements more consistent. So basically, what I just said, we want to make sure we use short, well-matched, low-loss, shielded cables on the RF side. Low loss and short length is very important for our test setup. When you torque the cables, this is kind of important, as I mentioned in Part 1. Don't keep the cable under a state of torsion, because that's mechanical energy and that could be released as a phase pop or a phase perturbation. So just make sure that there's no torsional stress on the cable. We have the DUT in a suitable shielded room, shielded environment. It's well isolated from mechanical vibration, keeping the temperature and humidity controlled. And again, don't disturb anything or touch anything during the measurement. What we're going to just focus on now, again, the signal source output power from the instrument, from the phase noise test set, before it goes into our attenuator and fixed pad. And we're going to focus on the RF input back into the analyzer out of our DUT after the step attenuator and fixed pad. And you can see how we have it configured here. This works well for our setup. We find that we get the best performance if we keep the signal source output power fixed, and then we vary the DUT input power using a combination of the fixed padding and the step attenuator. Pretty much what I just said, I won't repeat it here. The one thing I will note is that we try and keep the power back into the analyzer within a fairly narrow range, as narrow as we can make it. And we found that somewhere between 7 to 13 is a reasonable range. We get very consistent, repeatable performance when we do that. So again, you all remember this from Part 1, courtesy of Professor Rubiola. And we focus predominantly on these two figures in Part 1. We talked about what is 1 over F noise, what is flicker noise, how is it generated, how does it get translated to my carrier. We talked about what is low power, what is high power, how do we discern between the two. So now we're going to look at cascading amplifiers. So we will look at a series and a parallel configuration. Again, we're going to use 4 here to try and accentuate the effect. And we know that in series, the 1 over F noise should degrade by 3 dB log base 2 of M. And then in parallel configuration, the 1 over F noise should improve by 3 dB times log base 2 of M. So let's see if we actually achieve that. Again, if you recall from part 1, the first thing we do is we measure our through path at the appropriate signal levels to get an idea what is the best we can do. This is our additive phase noise floor. And we've done it here because we're going to study 2 gigahertz and 6 gigahertz during this webinar. And you can see these are the noise floor. We're going to put little tick marks on each of the decade points, and we're going to show those tick marks in the measured data that includes the amplifier, so we can get an idea whether we're at the noise floor of the instrument or whether we're above the noise floor, and if so, how much. So the first thing we're going to do is look at I'm just going to take 2 identical amplifiers and just connect them back to back. Nothing in between. And this notation will be used. The X60-223 LPN happens to be this amplifier. It's an identical amplifier on the output. And in this case, we have a quote-unquote 0 dB pad, okay, interstage. Now, we chose this because it is based on, here it is, the LVA 273 PM Plus, which is the surface mount version of the MMIC we studied last time. So we're basically looking at the same part, just that now it's in a connectorized format. This slide format is going to be repeated throughout the webinar. And basically, we have the single stage, the single device, outputting output power and gain. And on the right, we have the cascaded performance, output power and gain. What I would like you to pay attention to is the compressed gain, okay, in all these instances. Okay, the compressed gain, is important that we compare the different configurations in terms of what is my compressed gain. All right, over here, we have the input power to the first amplifier, its output power, and in this case, that is the input power to the second stage. And what we're going to do throughout the webinar is we're going to compare these ranges to our chart here of AM to PM distortion and compression. So for example, right now, about -5 to 5. So we're running in this region. And then the second stage is running way out here. So you can see in this case, the second stage is saturated. And the first stage is what we'll call small signal. Maybe a little compressed, but it's not saturated like we have here. And we're going to see how, as we move these input power ranges into this region, how the AM to PM distortion could affect the additive phase noise performance. So the first thing we're going to do is we're going to look at the performance of the single stage by itself. That's where we get an idea. How is it doing? What is this performance? And I'm going to compare that to the cascaded configurations that we look at later on. So you can see here where it's pretty much behaving as it should. The 1 over F region is fairly insensitive to input power. The white noise region is improving with increased signal power, as it should, because the signal noise ratio improves. And we have our noise floor points indicated here. So you can see 100 hertz, 1 kilohertz. We are really being influenced by the test set noise floor. So we just have to accept that. And you can see if I keep increasing the power here at 2 gigahertz, this will continue to go down, but this is the limit that we decided to use for this experiment. Now we're going to look at the cascaded response. So here you see this, the first stage, the second stage, 0 dB, and what do we see? Well, we see an increase in the 1 over F noise of approximately 3 to 5 dB from 10 kilohertz down to 100 hertz. Now if we go back and forth, single. So we are basically following the theory, even though we're operating in a very different region, we're keeping that one part saturated, we see a degradation in the 1/F noise when we cascade the two amplifiers. Now, one question you should ask, well, is this the best I can do? Is that it? I'm stuck here. I can change my input power. What if I was able to customize the input power to the first stage and the input power to the second stage? Can I get a better solution? Let's find out. So now, what do? We put a pad between the two. So what we're doing here, this is the same, okay? So the input power to the first stage is the same, of -5 to 5. We're still at 2 gigahertz, where, as you can see, our AM to PM is not really a factor. I can pretty much do whatever I want with this amplifier at 2 gigahertz without having to be concerned about AM to PM. But when we change frequencies, when we change carrier frequencies, you'll see that that's not always the case. So here we're running about 7 to 14. So we brought it from way back here back into this region. Notice the large signal gain really hasn't changed much. So what we did is we pulled the output stage way out of deep saturation and replaced that with the 6 dB pad. And by doing so, we altered the input power range into that amplifier. So what do you think we're going to get? Let's see. Again, here's our reference. Here's the single stage by itself. Here's 2 back-to-back with no padding. And now, look at that. Look at that. Look at the improvement we're able to achieve by adjusting the power levels into the first and into the second stage. Tremendous improvement. Now we're back to almost our theoretical degradation of 3 dB here. And again, at 2 gigahertz, we can keep going with power and fine-tune this a little bit more, because we're not really seeing the AM to PM effects at 2 gigahertz. But if you're going to do a cascade, notice the large signal gain didn't change. Our large signal gain was the same. Our saturated gain was the same. So if I'm designing an LO amplifier chain, I like this, but I want this curve. I want to get the best performance I can. And by optimizing that configuration, you're able to improve the performance by simply, by just cascading 2 amplifiers, hoping for the best. But it requires careful measurement and attention to find the optimum configuration. Now, let's look at 6 gigahertz and see if the story changes. So now we're going to look again at 6 gig. We're going to start off with the same configuration, a 0 dB pad. We're going to keep the input power range approximately the same, but now we're looking at this curve. You can see the 6 gigahertz curve corresponds to here. So again, -5 to 5, we're on the back end of this curve. The second stage, again, is saturated. Again, it's off the chart here. It's way down in the saturated region. So we don't expect to see much contribution from the second stage, but let's see. Notice our large signal gain, again, is about 20. Let's look at the single stage again, the single part by itself, similar input power range. And do we believe this? Could this be a little cross-spectral collapse maybe sneaking in? I left it in because you're going to see this. You may see these effects when you make these measurements. Is it really below the system noise floor? Probably not. I left it in just because you should be aware that this could occur, but we have to take it with a grain of salt. Now we look at the case where the two are just cascaded with 0 dB in between, and look what we see. It's pretty good, right? It's pretty good. We see about a 3 dB degradation, so that 3 dB log base 2 of M appears to remain valid even when you're not operating in small signal. At least that's what we're showing here. What we notice here, though, that we didn't see at 2 gigahertz is the white noise increasing. And we attribute that to the cascade analysis of noise figure. As you recall from part 1, when these devices are operated in saturation, the noise figure increases with input power, right? If you measure small enough signal level, say back here, you can use this power level to determine the noise figure based on the additive phase noise. As you drive that amplifier further and further into compression, that noise figure increases. So what we're seeing here is just the cascaded effects of the two amplifiers. We did not see this as much at 2 gig, we're seeing it at 6. But the 1/F does what we expected, it degrades. And it degrades by about 3 dB here. But again, same thing. Is this the optimum? Is this the best we can do? Let's try that same experiment where we change the interstage pad to 6 dB. Again, the large signal gain is roughly the same. We lost maybe 1 dB here, not even. So what we did is we pulled that second stage out of saturation and replaced that loss with a fixed pad. So now, going into the second stage, we're 6 to 14. But for 6 gigahertz, 6 to 14, that's kind of in the sweet spot of this AM to PM distortion. The first stage is still on the back end, but the second stage now is in the middle. So we expect to see worse performance. Let's see if that's the case. So again, here's our reference. We're gonna just keep this in mind. We're gonna be comparing against this. Notice it's mostly noise floor up until almost 100 kilohertz, so nothing you can do about that. But here's our back-to-back with 0 dB padding. Okay, so we see the increase like we expect. Now we put our 6 dB pad in, and look at that. Look what you get here. Again, you get an optimum level where you get almost no degradation. There will be some, obviously, but you get minimized degradation when cascading 2 stages if you can adjust those power levels and keep it out of that region. So if you look here, notice this is not the highest power level anymore. This corresponds to minus 0.89 dBm. So if we go back a couple of slides, this row here appears to give us the best overall performance. Well, let's take a look at that. -1, all right, that's fine. I'm no AM to PM there. +10, well, I'm kind of on the other end of that curve now. So I missed the peak. All right, I bypassed that peak by adjusting the power levels accordingly. So you get it's very consistent with our theory that we want to avoid this peak here. So if we go back again, so okay, this sounds good, but wait a minute. Let's say now I want to design a broadband LO amplifier that's operating from 2 to 6 gigahertz. And I have a source that's outputting plus 10 dBm, and that source is flat from 2 to 6. Well, what do? I don't want that. I have to change these. I need a slope. I need to decrease my power going into my amplifier chain at 6 gigahertz. I need to raise it at 5. Well, to go from 10, for example, 10 to 4, that's a fixed pad, right? So that's easy. I put a fixed pad on the output of my synthesizer, which is always good practice anyway. But then how do I get this slope? Well, coincidentally, we have these reflectionless filters at mini circuits, which are matched in the reject band. And I did a little ADS simulation where if I cascade 2 XLF312H plus reflectionless filters, these are mimic filters in QFN style packaging, the surface mount. Notice I never degrade my return loss, even as I start to reject to worse than 15 dB, so it's well matched. But I get almost the slope that I need into the amplifier so that I'm achieving the best additive phase noise performance over that frequency band. So you can optimize this chain over a wide band, provided you can adjust your power levels to what you measured for each stage. So this is very interesting, and it's a key attribute that one can design a broadband system while maintaining the best additive phase noise across that band, but it requires measurement and some thought and some equalization. Again, we see a little bit of a noise figure rise here due to the cascaded effects, but nothing we can do about that. So this kind of summarizes the different scenarios, the different cases that we just looked at. So we're going to be referencing the single stage here in small signal versus small signal to saturated, small signal to saturated at 2 gigahertz and 6. And nice way to show these lines are intersecting the single stage, and coming over here, you see the 1 over F increasing. You see the 1 over F increasing here, a little bit less here than here, but that's what one would expect. All right, that's what one would expect from that. We're seeing the noise figure increase at 6 because of the cascaded effects. So compared to the small signal, we're seeing some degradation as one would expect. Now, what about when we compare the single stage versus the case with the 6 dB pad interstage? Now we see, look at that. If I pick the right power level, I get much less of a degradation when I cascade the two stages if I adjust the power level accordingly. And the same is true at 6 gigahertz. It's just that the power level is different. So I need to equalize to get the appropriate, I'll call it optimum power into the chain at both 2 gig and 6 gig. And this is about the best you can do here. And again, it's within theoretical bounds, and it's a great way to avoid unnecessary distortion caused by you operating in a region of high AM to PM distortion. So one more comparison showing the 0 dB case versus the 6 dB case at both frequencies. And you can see here, it's clear I'm able to do a better job at 2 gigahertz and a better job at 6 gigahertz compared to just blindly cascading two amplifiers by careful measurement and careful control of the power levels into each stage. Now we're going to look at parallel. I picked 4 because I want to make sure I can really demonstrate the improvement that one would expect by paralleling amplifiers. So here we have the same amplifier, the ZX60223 LPN, which is the LVA 273 PM plus, and connectorized between splitter and combiner. So the input powers here are now referenced to the input of the first splitter. The output powers, notice these output powers, which are the powers into each amplifier, are consistent with what we just looked at. So notice -5 to 6, that's pretty much what we just evaluated in the series combination. So we're comparing apples to apples here. Here's the output powers, again, from each stage, and then when they combine, you get the final output power here. And again, same type of an arrangement, about 15 dB large signal gain. We have our AM to PM curves, which didn't change because they're based on this amplifier. So let's see what happens when we measure the phase noise through this cascade over these power levels. Again, we're operating at 2 gigahertz over here, and then well above, well, almost off the chart here. So again, it's basically small signal and saturated. This is our reference, single device, okay, but mostly noise floor limited here. When we go to the 4, we expect to see an improvement. We expect to see 6 dB. Will we? I don't know. We're kind of sitting on the noise floor here, so let's see what happens. Yeah, all right. I got some improvement. I can't demonstrate the 6 dB because I'm limited here. But what we'll study in part 3, I'll give you a little hint, is cascading a single device with the 4 in parallel. And then you'll be able to see the true effect of combining in parallel versus series. So unfortunately, we can't see a lot of improvement here because we're still kind of sitting on the noise for a little bit here. Notice our noise figure remained about the same. So the power levels are a little bit different, but we can't really demonstrate the improvement, but we can infer that improvement later on when we get into part 3. So now we're going to do the same thing at 6 gigahertz. Again, similar power levels into and out of each stage. We're basically operating up to +5, again on the back end of that AM to PM distortion curve, and +10 and above. So we're, again, out of the region here. Again, there's our single stage, and there's our 4. And again, we're kind of test set limited here. We can't really demonstrate the true performance we're actually achieving, but hopefully we see that in part 3. So let's just compare single to 4 combined, 2 gigahertz and 6 gig. And again, you just kind of follow the lines over. You can see it's the same to a little better. It's the same to basically the same. So we can't demonstrate the improvement here, but there's certainly no degradation. And we'll just have to accept that for right now until we get into part 3. So that's all we wanted to get to today, because there's a lot of material if we combined part 2 and part 3. So we felt it'd be better to just split it into two different webinars. But I encourage you to go back and review part 1, review part 2, and you'll have a much better understanding when we get into part 3, which we will be releasing at some point. Again, these are the references. Hopefully these are a little bit clearer than the references presented in part 1. They're the same references, but we had some comments that they were hard to read. Hopefully you can read these now. If not, just email the applications department and they'll provide you with a better copy of these references. So again, thank you for your attention. I hope you enjoyed part 2. Thank you.